Good afternoon, everyone. I hope that you're having a great week. Today we will finish off with differentiation of logarithmic and exponential functions. And tomorrow we have a Google Meet if you have any questions from any of the previous lessons that we've been covering. And Friday, of course, is a professional development day for teaching staff, so there's no responsibilities for the students on that day. So you've got a long weekend coming up. This lesson is on page 14 of your current lesson handout. And as a warm-up, we're going to determine the derivative of a number of different functions. And the first function is this function. And that is pronounced ln x. That's how we pronounce it. And that symbol, ln, is referred to as the natural logarithm. And in Monday's lesson, we learned that there was a natural base in exponential functions, and the base is base e. Well, that's what this is in reference to. When you see y equals ln x, that means y equals log base e of x. So it's a base e logarithm. So we have to differentiate this. I'm just going to rewrite it as y equals log base e of x. And I'm going to remind you of something from Math 30-1. When you have a logarithmic expression or equation and you don't know how to proceed, it's best to write it in exponential form. So remember that when you have y equals log base b of x, that means that the base raised to y is equal to x. And although you do not know how to differentiate a logarithmic expression, you do know how to differentiate this expression. The derivative of the left-hand side, well, the left-hand side is e to a function of x. We learned on Monday that e to the function of x has a derivative of e to the function of x multiplied by the derivative of the function of x. And on the right-hand side, we have x. And the derivative with respect to x of x is 1. So what we end up with when we rearrange that for dy dx is we end up with 1 over e to the y. But e to the y is x. Since y equaled the natural logarithm of x, that means x is e to the y. And that means that the derivative that we've determined is 1 over x. So what have we learned in this warm-up? In warm-up A, we have learned that the derivative with respect to x of the natural logarithm of x is 1 over x. So from now on, whenever you have to differentiate the natural logarithm of x, you know it equals 1 over x. Let's take a look at the second part to the warm-up. Y equals log base 2 of x. Well, let's rewrite this in exponential form. 2 to the y is equal to x. And now what we're going to do is take the natural logarithm of both sides. When I take the natural logarithm of 2 to the y and set it equal to the natural logarithm of x, I can, on the left-hand side, move that exponent of y out in front because we have this rule which is called the power rule for logarithms. Log base b of a raised to the m is the same as m multiplied by log base b of a. We're always allowed to move an exponent on an argument of a logarithm down in front. I just want to point out to you, this has nothing to do with differentiating. We're going to move that y in front simply because we're allowed to with logarithms. And that gives me y multiplied by the natural logarithm of 2 equals the natural logarithm of x. So if I rearrange this for y, I get y is equal to 1 over the natural logarithm of 2 multiplied by the natural logarithm of x. And we can very easily differentiate that. On the left-hand side, the derivative of y is the derivative of y. It's dy dx. Now, we learned a long time ago, I'm looking at the right-hand side now, that when you have a constant, and 1 over ln 2 is a constant. 1 over the natural logarithm of 2 is a constant. When you have a constant multiplied by a function, ln of x is a function, the derivative is equal to the constant multiplied by the derivative of the function. Well, ln of x has a derivative of 1 over x. And we can simplify that by writing dy dx equals 1 over x ln 2. So what have we learned in this specific part of the warm-up? We've learned that when you want to differentiate with respect to x, a log base 2 of x, you're going to get 1 over x ln 2. Now, what have we learned in a more general sense? Well, we could try the same thing with log base 3 of x and log base 1/2 of x. What we have learned is the derivative with respect to x of log base b of x is 1 over x ln b. From now on, then, you can use that rule. What is the derivative of log base 10 of x? It's 1 over x ln 10. We have one more to go, and then I'm going to summarize everything that we've learned about derivatives of exponential and logarithmic functions. What if I ask you to differentiate y equals 2 to the x? Well, you don't have a rule for that. You know how to differentiate e to the x, but you don't know how to differentiate any other base to the x. Let's start off by taking the natural logarithm of both sides. I can now rewrite this as the natural logarithm of y is equal to x multiplied by the natural logarithm of 2, and I can differentiate that. The derivative of ln of y is 1 over y dy dx. And when you take a look at x ln 2 is merely a coefficient. Of x. So if I said that we had an expression that was 5x, and I said, what's the derivative of 5x? You would say it's 5. If I had pi times x, the derivative of pi times x with respect to x is pi. So the derivative of ln 2 times x is ln 2. And now I can rearrange for dy dx. Dy dx is equal to y ln 2, but y is 2 to the x. What have we learned specifically in part C of the warm-up? We've learned that the derivative with respect to x of 2 to the x is 2 to the x ln 2. I don't know if you remember, but in the previous lesson, we found the derivative of 2 to the x using the definition of a limit, and we had the derivative with respect to x of 2 to the x was approximately equal to 0.69 multiplied by 2 to the x. Well, I've just figured out with you in warm-up C that the derivative with respect to x of 2 to the x is 2 to the x ln 2. Well, this is exactly equal to the natural logarithm of 2. On your calculator, you have a button that is the natural logarithm. It's right below your common logarithm button, and if I find the ln of 2, I get 0.69314. I don't know if you recall, I think you probably do, that when we found the derivative with respect to x of 3 to the x, we got approximately 1.1 multiplied by 3 to the x. And if we follow this pattern that I have for 2 to the x, if the derivative with respect to x of 2 to the x is 2 to the x ln 2, then the derivative with respect to x of 3 to the x is 3 to the x ln 3. Well, ln 3 will give you that 1.1. And that means, going back to C, yes, specifically, we have learned this in warm-up C, but what we have learned in general is the derivative with respect to x of b to the x is equal to b to the x ln b. And that pretty much concludes all of our differentiation rules in this course. We started off by learning about the power rule, where you wrap an exponent around a base, which is a function of x, and then you drop 1 from the exponent. We also added to that the chain rule, that you would have to multiply by the function of x, which was the base. We also learned along the way that there is a product rule and there is a quotient rule. We also learned about trigonometric derivatives. So you can differentiate now any trigonometric function, of course remembering to use the chain rule whenever applicable. Now we've learned specifically how to differentiate e to the x, b to the x, log base b of x, and log base e of x. But we can customize those now to include the chain rule. So starting off with what we learned on Monday, we learned that the derivative of e to the x was e to the x. When we combined that with the chain rule, we learned that the derivative of e to the u is e to the u du dx, where u is a function of x, where the argument of that operation is a function of x. We just learned in warm-up C that if you had a base that was not e, the derivative of b to the x is b to the x ln b, but if we combine that with the chain rule, the derivative of b to a function of x is b to the function of x times ln of b times the derivative of the function of x. At the beginning of this lesson in warm-up A, we learned that the derivative of the natural logarithm of x is 1 over x. Well, that must mean when we combine that with the chain rule, the derivative of the natural logarithm of u is 1 over u du dx, where u is a function of x. In other words, you multiply by the derivative of the argument. And in part B of the warm-up, we learned that the derivative of log base 2 of x was 1 over x ln 2, which means if we want to find the derivative of log base b of a function of x, it's going to be equal to 1 over u ln b times the derivative of the function of x. Again, the chain rule should be making sense to you now as simply saying you always multiply by the derivative of the argument. When I take a look at this statement, we are differentiating this operation. When I take a look at this statement, we are differentiating this operation. This statement is talking about the derivative of this operation, and the final statement is talking about the derivative of this operation. In each of the operations, there is an argument. The argument here is u. The argument here is u. The argument here is u. And the argument here is u. So in each differentiation rule, you multiply by the derivative of the argument. That's the bottom line with the chain rule. We can forget about saying things like, oh, we have to multiply by the derivative of what you wrap the exponent around. Or saying something like, we have to multiply by the derivative of what you were taking the sign of. We no longer need to say you have to multiply by the derivative of what e was raised to. The chain rule says in its purest, most simplest form, you always multiply by the derivative of the argument. All right, let's use these 4 rules now. And by the way, if you were to go to the classroom folder, there was a file there called Trigonometric Derivatives, I believe. Now there is a file called Derivatives. And if you open that file up, you will find, among other pieces of information, these 4 rules. And you need to have those 4 rules in front of you. Before we go on, I guess I want to point out one more thing. If you know that the derivative of e to the u is e to the u times du dx, you can use that to find any of these other derivatives, just like we did in the warm-up. I bring that up because in post-secondary, you're probably not given formulas like this, but if you know that the derivative of e to the u is e to the u times du dx, you can use the strategies we looked at in the warm-up to find the derivatives of any of these other things. All right, let's take a look at some examples now. Determine dy dx in each of the following cases. Now, one of the things you'll notice, let me rewrite this, is that we very often put absolute value signs around the argument of a logarithm in this course. And the reason for that is that you're not allowed to take the logarithm of a negative number. Because we have weeded some things out of Math 30-1 and weeded some corresponding things out of Math 31, all I will say to you is it's unimportant. Don't worry about the absolute value signs. If they're there, great. If they're not there, it doesn't matter. All right, so what is the derivative of y equals ln of 2x squared minus x? Well, from your formula sheet, or probably from memory after today, the derivative with respect to x of the natural logarithm of a thing is 1 over that thing times the derivative of that thing. You will remember that the derivative of ln of x is 1 over x. You will know that pattern. Because we know that's the case, the derivative of this expression will be 1 over 2x squared minus x, 1 over the argument, multiplied by the derivative of the argument. And the derivative of 2x squared minus x is 4x minus 1. And that means the derivative dy dx in this example is equal to 4x minus 1 over, I suppose we should factor the denominator and take an x out and be left with 2x minus 1. We're factoring it because expressions are simplifiable once you've looked at them in factored form. Turns out this doesn't lead anywhere, nothing cancels, but that's the answer. What about the derivative of y equals x squared ln x? Well, it is a product. Let me write it explicitly as a product. X squared times the natural logarithm of 2x, and there I go. I've dropped the absolute value signs. It's really not important. I need to use the product rule. Dy dx equals 2x, which is the derivative of the first, multiplied by the second, plus the first, which is x squared, times the derivative of the natural logarithm of 2x, while the natural logarithm has a derivative of 1 over, times the derivative of the argument. The argument was 2x, the derivative of that is 2. Now we can simplify this a little bit. We've got in the second term a couple of things that cancel, an x and a 2, which gives us dy dx equals 2x ln of 2x plus x. So dy dx equals x multiplied by 2 ln of 2x plus 1. All right, and let's take a look at example C. The derivative with respect to x when y is equal to ln x over x to the 4. This is going to require that we use the quotient rule. Dy dx is the derivative of the top, which is 1 over x, multiplied by the bottom, which is x to the 4, minus the top, which is the natural logarithm of x, multiplied by the derivative of the bottom, which would be 4x cubed. This, of course, is over the denominator squared. And the denominator is x to the 4, so it's over x to the 8. This is going to give us in the numerator x cubed minus 4x cubed ln x over x to the 8. Pretty simple question, actually. There's just another step that has to be done for us to see what the answer is going to be. I can factor out an x cubed out of the numerator and be left with 1 minus 4 ln x. And it's over x to the 8. So dy dx, when we cancel the x cubed on the top with an x cubed on the bottom, will be 1 minus 4 ln x over x to the 5. And that's the answer to example C. All right, D. We're going to have to use the product rule. We have a function that is a product of 3 to the x and x to the 3. Be very careful here. When you differentiate 3 to the x, you don't use the power rule. 3 to the x is not a power. 3 to the x is an exponent. X cubed is a power. 3 to the x is exponential. So the derivative of 3 to the x is 3 to the x ln 3. How do I know that? I know that because if I look at a formula sheet, the derivative with respect to x of b to the x is b to the x ln b. Now after a while, you may not have to look at a formula sheet because you will remember it, but that is on a formula sheet. So that is just the derivative of the first. We still need to multiply by the second, and then we need to add the first, I'm using the product rule, remember, multiplied by the derivative of the second, which is 3x squared. So this is the derivative of the first. This is the second. This is the first. And that's the derivative of the second. What does that leave me with for dy dx? I'm going to factor out the common factor of 3 to the x and the common factor of x squared. Out of the first term, I am going to have an x left and a ln 3. Out of the second term, I'm taking a 3 to the x out and I'm taking an x squared out. All that leaves me with is the 3. And that's the answer to D. E, the natural logarithm of x plus 2 over x minus 2. Well, the derivative with respect to x of a natural logarithm is 1 over the argument multiplied by the derivative of the argument. This is the argument, so I need to use the quotient rule. The derivative of the top multiplied by the bottom minus the top multiplied by the derivative of the bottom over the bottom squared. So what can we do here? Well, one of the things we can do is take this first part of our derivative, which is 1 over a fraction, and rewrite it as the reciprocal of the fraction. The other thing we can do is simplify the top of this second part. And if I expand it out, I will have x minus x, which is 0, and negative 2 minus 2, which gives me negative 4. And then on the bottom, I have x minus 2 squared. And now I can simplify this and end up with dy dx equals negative 4 on the top, and then on the bottom, x minus 2 and x plus 2. We have an x minus 2 in the numerator on this line, and we have an x minus 2 in the denominator, so we can cancel them, leaving a single x minus 2 in the denominator. I want to show you one other thing here. We were trying to differentiate this expression, y equals ln x plus 2 over x minus 2. Now, using your laws of logarithms, I can write this as the natural logarithm of x plus 2 minus the natural logarithm of x minus 2. A logarithm of a quotient is a difference of logarithms. If we differentiate from here, the derivative of ln of x plus 2 is 1 over x plus 2 times the derivative of x plus 2, which is just 1, minus the derivative of the ln of x minus 2 is 1 over x minus 2 multiplied by the derivative of x minus 2, but that's 1 again. And what we end up with is dy dx equals 1 over x plus 2 minus 1 over x minus 2. Two rational expressions like this would have a common denominator that's the product of them. And what that would entail in converting them to that new denominator is that I would have to multiply the numerator and denominator here by x minus 2, and I would have to multiply the numerator and denominator here by x plus 2. So what I would get on the top would be x minus 2 times 1, which is x minus 2, minus 1 times x plus 2, which is minus x plus 2. Well, this is going to give you, for dy dx, negative 4 over x plus 2, x minus 2. And that's what we got when we did it the other way. Again, one of the things I love about math, as long as you follow the rules, it doesn't matter what path you take. There's no subjectivity here. You get the right answer. On page 383, questions 1, 3, and 4 are a list of suggested problems. And once again, everybody, you know the drill. We have a Google Meet tomorrow, so if you have any questions and are available during that time, feel free to drop in and I will help you out. If you can't make it during that time, remember you can email me at any time, and as soon as I get the email, I will get back to you and help you out. If I don't talk to you tomorrow, have a great weekend, but in the meantime, have a fantastic rest of the day and take care of yourselves. We'll talk to you soon.